On today's video, I'm going to be talking about resistors, voltage, and current. Really not interesting, but very, very important to projects. I'll talk about how resistors work, the relationship it has between voltage and current and resistance, and why you should care. First, let's start by talking about voltage, current, and resistance as they relate to each other. Ohm's Law is a relationship that shows that voltage is equal to current times resistance. A lot of people don't realize what the difference between voltage and current is, and it's a very important one. Voltage is essentially how hard you're pushing the electricity. How hard are you trying to push it through whatever it's going through? Current is how much are you actually getting through there for how much you're pushing. And resistance is how hard is whatever you're pushing it through pushing back at you. Let's look at some examples that can demonstrate these. Here's a simple example with a resistor connected through the positive rail, through the resistor, back to ground. If you haven't seen my breadboards video yet, you should check it out and make sure that you understand how breadboards can connect components together. In this example, I've set my power supply to 5 volts and I have a 100 ohm resistor in series. I've now connected my multimeter in series with the resistor to measure current. You can see we have 45.6 milliamps here, which is just about exactly what we expect to see. Because we want the current, and we know the voltage is 5 volts, and the resistance is 100 ohms, we can see that those two numbers divided will give us 0.05 amps, which is actually 50 milliamps. Very close to the 45.6 that we got. Now I've swapped the 100 ohm resistor out for a 200 ohm. And if we turn on the power, we see we get 22.7 milliamps, which makes sense because we've doubled the resistive force pushing back on the voltage, and thus we have half of the amount of current flowing through. This is obviously important because it means we can limit the current to certain devices, and by removing resistance, we can allow more current to flow through other devices. And again, if we go through our calculations, this makes sense with our law. Current is equal to voltage over resistance, and if you divide 5 by 200, you get 0.025 of an amp, or 25 milliamps. Now say we wanted more current to flow through there. How could we do that? Well, of course, we could increase the voltage. Now I've set my power supply for 10 volts. Let's see what we get for current. 46.7, very similar to the 44 we had before. Why is that? It's because now that we've doubled our voltage and our resistance from our initial step, we've got the same current as we originally had. Here's a simple design question for a simple resistance circuit. A heating element has a resistance of 900 ohms. You've measured that with your multimeter, and you need to create enough heat for your fish tank. It requires 6 amps of current flowing through. How much voltage should you supply? We know that voltage equals current times resistance. So if we want a voltage, and we know how much current we want, and we know how much resistance we have, we can simply multiply them together. For this particular heating element, for such a coil, you would need 5,400 volts. That's not reasonable. But this is a very good example of how you can find a very simple calculation like this incredibly useful. From this, we could now realize that we need a much lower resistance heating coil. At home, we have 120 volts, and our circuit breakers can take up to 15 amps. So the most power we could possibly draw, we can calculate very easily. Resistance equals voltage over current. We know that our voltage is 120, and our maximum current is 15 amps. So 8 ohms is the smallest resistance we could put onto our walls without tripping our circuit breakers or blowing our fuses. So why should we ever care about voltage, current, and resistance? We might care because sensitive components like transistors, MOSFETs, and inductors all have sensitive voltages and currents. So whenever we want to use them in our circuits, we have to be wary of how much current and how much voltage is getting to each of them. How much power do I have access to? Will I blow the fuses in my house or the breakers? How much power does that battery I'm using to control this robot have? And finally, microcontrollers, like Arduinos. They have sensitive inputs and outputs, which can be busted if we don't supply them the correct amount of current or voltage. Hopefully now you know a bit more about voltage, resistance, and current, and why they're useful to us. Thanks for watching.